you should have this note taker to take out today to take notes on. So we're going to start with our question of the day. I would like you to pause this video and take a moment to fill in these pieces of information in review of what we learned on the atom last week and last month. Okay, so now that you've taken a moment to do that, let's go through this. Your atomic number for fluorine is 9. The atomic mass is 18.99. We're going to round that mass number to 19. To find the number of neutrons, we take the mass number, and we're going to subtract the number of protons, because that's how many particles are in the nucleus. So when we do 19 minus 9, we get that there's 10 neutrons. We know that the number of protons and the number of electrons is always the same as the atomic number. And we're going to start to put those electrons onto our rings. So on the first level, it can only hold 2. We've used 2 out of our 9 electrons. On the second level, we're going to put the extra 7. Now, due to the rule of 8, we know that it could fit up to 8 electrons, but we already ran out, so there's no more on the third energy level. The total number of valence electrons, how many electrons are on that outermost level, is going to be 7. When you take a look at your periodic table of elements, we see fluorine over here in group 17, our halogens. So if we look at our oxidation number, which we've already labeled on our periodic table, we can see that for every element in group 16, the oxidation number is -1. But if we think about it, it also makes sense. Fluorine is in group 17, which means it has 7 valence electrons. It's going to be a lot easier for fluorine to steal 1 more electron to equal that happy rule of 8 than it would to give 7 away. If you like to steal electrons, you're negative, and fluorine only needs to steal 1 of them. So let's draw this fluorine atom. We're going to start with our element symbol of F and label that we have 9 protons and 10 neutrons. And with that, we have everything that should be inside of the nucleus. So we can start to create our rings of electrons. In our first ring, we can only hold 2 electrons. As we move to our second ring, we're going to have to fill in the other 7 valence electrons that we have. So we have 1, 2, 3, 4, 5, 6, and 7. So how many valence electrons does every element, except for hydrogen and helium, need in order to become stable? And by stable, I mean happy. And that is 8. This is known as the rule of 8 because all the valence electrons we need to completely fulfill an atom must be 8. So now we talked about ions before we left for spring break, but we're just going to review it. So an ion is defined as an element that does not have the same number of protons and electrons. And this can happen when we start to have bonding and some atoms are giving away their electrons to others versus some atoms are stealing electrons. It leaves an atom as an ion with an overall either positive or negative charge. For example, if we look at beryllium, how many valence electrons does beryllium have? Beryllium is in group 2 on our periodic table, so we can rightfully assume that it has 2 valence electrons. Will beryllium give away electrons or take on electrons to fill its energy levels? Well, if it only has 2 valence electrons, it's going to be a lot easier to give those 2 away than to get 6 more. So it's going to give those away, which gives it an oxidation number that feels really positive and happy to give them away of +2. Now there are 2 different types of ions. There's either a cation or an anion. A cation is a positively charged ion, which if it's positive, chemically speaking, that means it has more protons in the atom than it does electrons. Now, for this, you can look at groups 1, 2, and 13 as all being cations. You can remember this, and you can also know that Miss Doocy loves cats, and cats make you feel really positive because they're the best. So cats are positive. They're the positively charged ions. Versus an anion is a negatively charged ion, which means that chemically it has more electrons than protons. We see this in groups 15, 16, and 17. So you should take out your colored periodic table. Pause if you have to look around for it. You already have the oxidation numbers filled out. So let's look at which one of these are cations and anions. Groups 1, 2, and 13 are all positive. They have more protons than electrons, so these are cations. Group 14, the carbon group, has an oxidation number of either positive or -4. Sometimes it's a cation, sometimes it's an anion. We're not going to go into the specifics of which it is when. And then you see groups 15, 16, and 17 are all anions because they are negative. They have more electrons than they do protons. This last group, our noble gases, is never going to have a charge. It's not going to be a cation or an anion because it equals the rule of 8 and it's always happy and it doesn't need to steal or give away any electrons. What do you do if you're a sodium atom? You have 11 electrons, one too many to have an entire shell filled. You need to find another element that will take that electron away from you. When you lose that electron, you will have full shells. Whenever an atom has full shells, we know that it's happy. So let's look at chlorine. Chlorine has 17 electrons and only needs one more to fill its third shell and be happy. Chlorine will take your extra sodium electron and leave you with 10 electrons inside of 2 filled shells. You're now a happy atom too. You are also an ion and you're missing 1 electron. That missing electron gives you a positive charge. You're still the element sodium, but you're now a sodium ion, Na+, and you have 1 less electron than your atomic number. So now you've become a sodium ion. You have 10 electrons. That's the same number of electrons as neon, but you aren't neon. Since you're missing an electron, you aren't really a complete sodium atom either. As an ion, you're now something completely new. Your whole goal as an atom was to become a happy atom with completely filled electron shells. Now you have those filled shells. You have a lower energy. You lost an electron and you are happy. So what makes you interesting to other atoms? Now that you have given up the electron, you are quite electrically attractive. Other electrically charged atoms, ions, and opposite charge, negative, are now looking at you and seeing a good partner to bond with. That's where chlorine comes in. It's not only chlorine. Almost any ion with a negative charge will be interested in bonding with you. So let's see if you're listening to my story. A little true or false for you. 1. True or false? Cations tend to bond with anions. And 2. True or false? An atom without a positive or negative charge can bond with another atom. Both of these are true. As you saw with the example of sodium and chlorine, one of which is a cation, one of which is an anion, they tend to bond with each other. But you don't have to necessarily have a positive or negative charge to form a bond. Bonds can form when electrons are either transferred or shared. Now we're going to look at a new way to represent this information. And we're going to start learning about a Lewis dot structure. So first, let's just see what a Lewis structure is. It's A Lewis structure, also called an electron dot structure, is a structural formula in which electrons are represented by dots. Two dots between atoms represent a bond. It was named from Gilbert Newton Lewis, who introduced it in 1916. The importance of a Lewis structure is that they're very important for predicting geometry, polarity, and reactivity of many compounds. So how do we draw Lewis structures? For individual atoms, the Lewis structure is drawn by first writing the element symbol. And then you place a dot around this element symbol for each valence electron available. There are 4 positions for dots to be placed. Most chemists draw them on the top, bottom, left, and right of the atom. Each of the 4 positions must receive 1 electron, or 1 dot, before any electrons can be paired with one another. This is due to the rule of 8. This rule of 8 states that in forming compounds and atoms, they must gain or lose or share electrons to give a stable electron configuration characterized by 8 valence electrons. At this point, you should be here on your note sheet. We're going to answer this question and walk through a few element examples. When drawing a Lewis dot structure, you must have 2 really important things: an element symbol, and you must know the number of valence electrons. So the first thing, and you're going to kind of follow through these examples with me, is to choose your atom and write down the element symbol. We're going to start with calcium, which is an element symbol of Ca. The next thing you need to do is count the number of valence electrons. I have a trick by looking at my periodic table. Since calcium is in group 2, I know it only has 2 valence electrons. I need to distribute those evenly across the 4 locations. You can either go to top, bottom, left, or right. I'm going to start by putting 1 electron on one side of calcium and the other valence electron on the other side. And that completes my Lewis dot structure for calcium. Let's try oxygen. I have my element symbol O. If I look on my periodic table to count my number of valence electrons, since it's in group 16, I know that there are 6 valence electrons. To distribute the electrons evenly, I'm going to go 1, 2, 3, and 4. I have to fill in all 4 slots around the element symbol first before I start doubling up and pairing the dots, in which I will go 5 and 6. So let's walk through 4 more examples. We have boron, fluorine, potassium, and carbon. I also, in this case, want to start looking at what the oxidation number for all of these atoms are, because it's going to help me when I want them to make their perfect match and pair. So boron has an oxidation number of +3, and it has 3 valence electrons, which would create a Lewis structure like this. Fluorine has an oxidation number of -1, and it has 7 valence electrons. And as we put them around fluorine, they should look like this. You have 6 paired electrons, 1 that is unpaired. Moving to potassium, our oxidation number there is +1. For potassium, it only has 1 valence electron, and so we can place it anywhere around the element symbol of K. Carbon could have an oxidation number of either +4 or -4, and it has 4 valence electrons, which we will evenly distribute around the element symbol. Now you should be looking at this table on your note sheet. We want to use the oxidation number and the Lewis dot structure to help us figure out how many of each element it's going to make to take. Now you should be at this point on your note sheet. We want to use the oxidation number and the Lewis dot structure to determine how many of each element it's going to take in order to create a bond. So let's start by looking at magnesium and chloride. How many of each element are we going to need? Well, we have magnesium, we have chloride. The oxidation number for magnesium is +2. And the oxidation number for chlorine is -1. Magnesium is willing to give away its 2 valence electrons, while chlorine has 7 valence electrons, and it desperately needs 1 more. This -1 oxidation charge means that it would need another chlorine in order to be neutral with magnesium. Magnesium has a +2 oxidation charge, chlorine -1. In order to get those two things when you bond together to equal 0, you're going to need 2 of those chlorine atoms. This means that if we were able to write an element out in its chemical bond name, we would have magnesium chloride 2. So as you're filling in this chart, you should draw magnesium with its oxidation number above it and its Lewis dot structure. You're drawing chlorine and writing what is the chemical formula for this bonding of elements. So let's try another one. We have lithium and oxygen. In order to create a Lewis dot structure for lithium, I have 1 valence electron with an oxidation number of +1. For oxygen, I have 6 valence electrons with an oxidation number of -2. I see I have -2 for an oxidation number on oxygen, but I only have +1 for lithium. So in order for those to balance each other out and equal 0, I'm going to need 2 lithium. As you can start to see, we write these chemical formulas with subscripts. I've written lithium subscript 2 oxygen using their element symbols. What this tells us as a chemist is that in order to make this chemical bond, in order for it to be neutral, you must have 2 lithium and 1 oxygen. So I challenge you to pause here in this video and attempt the next 2 element bonds. Alright, now that you're back, let's check your answers. You should have these 2 Lewis dot structures, and they're actually equal to each other, so there's no need to have multitudes of each element. You only need 1 for the chemical formula. For boron and oxygen, this one's a little bit trickier. We're actually going to need 2 boron and 3 oxygen in order to make the total charge of the bonds neutral. So you should have these pieces of paper out in front of you from your take-home packet. You see on the left we only have 2 slides of notes we're going to go through, and on the right is an activity that you're going to be completing for class today. So I'd like to start out with our question of the day, warm up our brains, start thinking about science a little bit, and we're going to review over some of the terms that we learned in our lesson when you last connected with me, in which that lesson was about what's an anion, a cation, and Lewis dot structures. So if you could pause this video, take a moment to work through the question of the day, and warm up your brain before we finish the rest of this lecture. So this first section is a matching section. So we're going to match an anion with D, a negatively charged particle. A cation is B, a positively charged particle. Group 2 would consist of C, a group of positively charged particles, and group 17 would be a group of negatively charged particles. Now I asked you to draw the Lewis dot structures for aluminum and arsenic, and I also wanted you to label them with the oxidation numbers associated with each. So for aluminum, you see that there's 3 valence electrons all evenly spread out around the element symbol, and we have an oxidation number of +3. For arsenic, our element symbol is As, and we put all of our valence electrons 5 of them evenly spread out. Only one of them is pairing because we have to fill in the 4 places first. Then we add that 5th one to the left there, and we also write in our oxidation number of -3. These would actually make a perfect pair coming together. You wouldn't need multiples of either of them. They would be a perfect bond, a cation and an anion, because together they would make a neutral charge of 0. We're going to learn about 2 different types of bonds today. There's one called an ionic bond, and there's one called a covalent bond. Now, if you ever take chemistry, you're going to go really deep into these topics. We're just brushing the surface, helping you become familiar with that terminology. So an ionic bond is a bond where electrons are being given away to one another. They're actually getting rid of the electron and giving it away. So for example, you have sodium and chlorine. Sodium has an oxidation number of +1. Chlorine has an oxidation number of -1. We've given this example many times in class, but in order to create a bond, sodium is going to give away one of its electrons to chlorine so that sodium can have completely filled outer energy levels and chlorine can have completely filled outer energy levels. Versus a covalent bond is a bond where electrons are shared between atoms. An example of this is water. Water consists of hydrogen, 2 of them, and an oxygen. Now those hydrogens, they only have 1 electron, and they don't want to just give it away to oxygen, they want to share with it. So you can see kind of the difference between these 2 diagrams. For hydrogen, they're hugging the same electrons together, they're sharing them, they're being very kind, versus for sodium and chlorine, sodium's just giving an electron away. So in summary, ionic bonds give away while covalent bonds share. So today you're going to be working on an activity. If you pull this out, and it's called Water, the Mickey Mouse Molecule. I'm going to read this introduction to you. Water droplets are round, but if you kept dividing one into smaller and smaller pieces, what would an individual molecule look like? Water, like all matter, is made of tiny particles called atoms. Atoms are made up of protons, which have a positively charged, electrons, which have a negative charge, and neutrons, which have no charge. Protons and neutrons are located in the center, or nucleus, of the atom, while electrons spin around the outside of the nucleus. Electrons are organized in energy levels. The closest level to the nucleus is only able to hold 2 electrons. The next level can hold 8. When a bond forms between 2 hydrogens and 1 oxygen to form a water molecule, a sharing of electrons occurs between the hydrogens and the oxygen. This sharing fills the first and only energy level in each of the hydrogen atoms, as well as the second energy level in the oxygen atom. Because both hydrogens are located near to one end of the oxygen, and their protons are nearest that end of the molecule, that end tends to be positively charged. The other end is negatively charged. This causes the water molecule to be called a polar molecule, and results in the strong attractive forces between water molecules because opposite charges attract. So this is what you're going to do today. From the following page, page 64, this one, where you see these cutouts for a molecule, you are going to cut out all the atoms, protons, neutrons, and electrons, and you're going to assemble a water molecule from those cutout pieces so that it resembles this diagram that's on the sheet of paper. When you're done, you're not going to be able to attach it to a classmate's, but I still want you to think about how would multiples of these water molecules attach together, thinking that the same rule applies that opposites attract, positive and negative being opposite. I want you to think about which side of this is more positive, which side is more negative, and where is it going to attach to. So you're going to cut all these out, and then submit a picture of your Mickey Mouse molecule that you're going to paste onto page 71. as well as a picture of your answers to the questions on page 67 into the Schoology assignment.